December 17th, 1903. The liftoff of the Wright Flyer over the sands of Kitty Hawk not only initiated the exciting history of manned flight, but it also brought scientists, engineers, and pilots face to face with some of the greatest challenges of the century. Since 1915, NASA and its predecessor NACA have been world leaders in solving many of these problems. Questions like how can our aircraft and spacecraft be quieter, faster, and bigger, all while protecting the environment. My name is Parker Vasic, and I am a NASA aeronautics scholar. This is the legacy I inherited as I completed my aerospace engineering degree at Georgia Tech. Growing up in the mountains of Roanoke, Virginia, I dreamed of inventing the next generation of aircraft and technology. Now NASA is helping me to do exactly that. This summer, I am an intern in the Hypersonic Air-Breathing Propulsion Branch at NASA Langley Research Center. My team is responsible for conceptualizing, designing, and testing some of the fastest aircraft ever to be flown. These hypersonic vehicles have flown over 7,000 miles per hour, or fast enough to travel the United States in roughly 25 minutes. Along with my mentor, Dr. Andrew Norris, I am supporting the Hypersonics team by developing new methods to model and simulate the burning of fuel in an engine, a process known as combustion. Now, one type of flame, called a laminar flame, is reasonably well understood. This is a flame like that of a steady candle. However, if that flame is blown on, the turbulent air interacts with and complicates the combustion process, making it much more difficult to simulate. I am responsible for developing a way to model both laminar and turbulent flames more easily. My work improves a suite of programs called Computational Fluid Dynamics, or CFD software. CFD is a powerful tool, as it can be operated by one engineer with a computer cluster, while traditional fluid analysis involves large-scale wind tunnel testing. Unfortunately, as a very complex computer program, CFD software may require hours or even weeks to run. My research may help to significantly speed up CFD programs, however, by identifying trends in chemical reactions and creating a surrogate model of the results. I am developing methods to model the reactions without having to run these computationally expensive programs. If successfully implemented, my work could significantly increase the capability and usefulness of CFD programs involved in chemical reactions. As aircraft become increasingly more complex, my work is something I may see used for the rest of my career. Working with NASA and the Hypersonics team has been an exceptional beginning to my career and entry into graduate school. I was able to work independently on my own research project, but had some of the world's best engineers right down the hall when I needed advice.